Okay, good afternoon, everybody. Sorry for being a little late. You can blame my fourth year class. So quick couple things. There is no Canvas quiz this week. Next one is going to open week of March 22nd, so you got a bit of a break. We're back on our normal drop-in tutorials, everything else next week. I know I feel like with you guys, we need to advocate for a March break in addition to a February break as well. So last class, we started into our journey functionalizing arene rings. So up until now, we've now introduced you guys to aromatic rings. These guys are specially stable. That's good. We can use it to do decorations and reactions in other parts of a molecule. The chemoselectivity is enhanced because of that. But there's also special reactivity if we have to functionalize it. So we introduced you, first of all, to phenols and phenoxides. This is where these are oxygen-type nucleophiles. These introduce carbon-type nucleophilicity, the carboxylations, and then finally oxidations, taking them up to quinones as a particular compound. And then finally now benzene. Now, if this is where we're talking about next to benzene, the benzylic type centers, and we talked about those couple reactions. So as a quick review, these are not know the mechanism. What are the products that you would get from these two kinds of reactions? Take a second, discuss it with your partner, and we'll talk about it in just a second. Okay. So this is a set of reactions that, again, you're not supposed to know the mechanism behind them. They're quite complex, and most of these ones are at least in the top one especially, these are radical generation mechanisms. What they require is carbon hydrogens at the benzylic center for us in order to break that benzylic CH, and that's the piece that we need to do sort of to get into the system to actually do chemistry. The first one is our chromic acid kind of conditions. This is the great reset or great leveler. It does an oxidation at the benzylic center, cleaving any of the carbons attached to it. And this is universal. It doesn't matter how many centers we have, we can actually remove all of those benzylic centers, cutting the carbon chain. The only limitation, what's resistant to this, would be tertiary centers, something where you have no CHs. On the bottom, we're treating it with a base. We have an oxygen nucleophile that's possible. This is relatively acidic, so we're making our phenoxide. Once we have the phenoxide, we can do SN2 type chemistry to make an ether. O, and then 1, 2, 3. How might I reset this back? What are the conditions that I would use to take a phenoxide back to, like the phenyl ether that I've drawn there? If I'm trying to set it back to the phenol and the alkyl halide, what conditions would I apply? Concentrated HBr, exactly. Very strong acid. What this is going to do is kind of SN1, SN2. We protonate the oxygen, turn that into a leaving group, and displace with our bromide. All right. So now we're going right at the aromatic ring itself. The functionalization we're going to talk about for the next couple of classes. And as a quick heads up for class planning, we are now down to roughly 3 weeks remaining. So we have next week, 3 classes. The week following, I have to go to San Diego on Monday. There will be no class on that following Monday, only 2 classes in the remaining week. The last week, so those are our 5 kind of programmatic ones. The last week, 3 classes we have in, those are going to be set aside as review, practice for structures, practice for things like synthesis. And then the last class, that last week in April, no class then, that's your first week of exams. So we'll take the pause at that point. So there's really only these 3 weeks left, 3, 2, 3. So as we go through this, the next thing we're going to focus on is how do we actually make direct changes on the aromatic ring itself. And that's going to be our nitration, sulfonation, and halogenation type reactions, what it looks like today. So the thing that's special about arenes are benzene-type systems, aromatic molecules. They are aromatic. That's what gives them their special stability. But the one thing you can kind of focus on, they are a giant bucket of electrons. Right? We have 6 pi electrons sitting here. So even though kinetically they're in a very deep hole, the aromaticity provides us a certain degree of stability, we can use that as a nucleophile. In the same way that oxygen has a lone pair and that allows us to use it nucleophilically, an enol or an enamine, remember it's a density of electrons there. It means it's a source for attacking electrophilic centers. Benzene can be thought of the same way, but it does require very, very special conditions. So if we can't really change anything about the nucleophilicity here, remember the strategies we applied for things like carbonyl activation. Strong base is useful because we can rip off a proton to make a oxygen minus, for example. That increases the nucleophilicity of the whatever the electron-rich thing is. Or the other option would be protonate the electrophile, or do something to the electrophile to make it even more positive. Benzene, we cannot make this thing any more nucleophilic. We can't add electrons into it very easily, which means we have to adopt the other strategy. We're going to take the electrophile and we're going to make it so electrophilic it has no other option other than to react with the benzene. So asterisks, the conditions we're applying here are meant to functionalize benzene, but you're using electrophiles that are so electrophilic they would rather do almost anything else. So this has to be done under careful selection where you're really limiting the options by taking simple aromatic rings plus very strong electrophiles. So we're going to be doing what we call electrophilic aromatic substitution. Again, that's your key there. You're going with very, very powerful electrophiles in order to substitute the ring, and you think of it where this is your nucleophilic component. It's because you have all these electrons there present that we're using them as our point. But they will temporarily mess up your aromaticity. So how this overall generic reaction can be thought of, what we're doing is something kind of like nucleophile attacks electrophile. Now, if you did this, right, if I just drew it as I've seen here, there's got to be some sort of an intermediate we form, because when we come out, we're losing a proton to give us our product. We've now formed a new carbon to electrophile bond, and we lose this proton. The point of that loss of proton is it allows us to regenerate our aromaticity. So what we're going to be doing overall is finding a very electrophilic molecule, exposing it under the right conditions to our benzene. We're using the double bond, the nucleophilic character of our arene to grab something to form this intermediate we'll talk about in a second. But that intermediate is not aromatic. It may be stabilized by their components, but it is not aromatic because we've had to use a double bond to break that sort of thing. We're going to have a temporary part where one of the carbons is like sp3, effectively. But by losing the proton from that intermediate, we can regenerate aromaticity. So if you think about an energy surface, what we're saying is I start super stable, aromatic molecule. I'm going to some very, very high level unstable intermediate, and then I kind of very quickly return to an aromatic molecule. So these have very high kinetic barriers, and it's only possible by pairing them with the right kind of electrophiling conditions. But we are going this very long detour, possible only because the products we generate in the end are once again aromatic. We're reusing that bond effectively, so we'll interrupt it temporarily. So the general mechanism, if we're just following out the arrows, you start with some super powerful electrophile. I'm going to do a nucleophilic addition onto here, and I want to highlight that there's a hydrogen at one of the centers. Again, there's at both, but let's pay attention to this one. When I do this, if you remember back to how you did, for example, HBr addition or bromination of double bonds, right? Back in sort of like 203, 233. If you took a double bond and you add an electrophile to it, what that's going to do is if I use that center, I have a hydrogen, I have an electrophile. What is left over here? Yes, I will leave behind a positive charge. Because what I'm doing is taking a double bond, the lone pair, and I'm associating that double bond, that's the only source of electrons. I am taking that double bond and temporarily passing it over to the carbon electrophile. That leaves a positive charge on the adjacent carbon. Again, the analogy here is, if you remember, double bond plus something like Br plus, you would normally add to this to form plus bromine, right? That's your electrophilic additions, or additions of electrophiles to double bonds that you've seen for olefination type reactions. It's also the reciprocal or backwards reaction for things like E1, right? E1 type mechanisms look something like this, going backwards. So great, we just made this. We kind of ruined our aromaticity, but there's something special here. What makes this at least allowable, or at least a little bit more favorable, that positive charge is not a localized positive charge. The positive charge there, we have interrupted it. It's no longer sp2 all the way around the ring, but everything else is sp2. I can draw resonance forms of this where my hydrogen electrophile is here, and I can delocalize that positive charge around the ring. That's one. There's one more. There's also a third. I could just hop it over this way. So I have my hydrogen electrophile, double, plus. What we're trying to highlight is what's special about this intermediate. It is a carbocation, but it is a resonance stabilized carbocation, at least. It's stabilized, so again, when you add the electrophilic center, wherever the electrophile adds, that becomes my sp3. It gives me a carbocation. That carbocation is going to be stabilized at least at 3 other centers. There's at least 3 other resonance forms that you will make, which means the overall structure, the kind of hybrid, you can think of these guys as my H, my electrophile, this, that is positively charged. I don't know if this will work, but can I rotate this? Oh, yeah. Took me all semester to learn I can do that. The reason why, this is how I remembered them. That is the coolest looking alien I've ever seen. But these are stabilized intermediates, right? You get this ring stabilized component. Yes, you've burnt aromaticity, bad. But at least you've got this kind of stabilization that's possible where you're delocalizing the charge over the ring in this way. You can think of it the other way we would draw this in terms of its relative charge. It is delocalized here, and it is delta plus, and delta plus at the ortho and para positions. That's going to come back later in terms of our stability, because anything that helps us at those specific positions to stabilize this resultant charge will help us with reactivity as well. It all couples together. Okay, so the overall generic step, this is step 1. You generate a carbocation. You generate a resonance stabilized carbocation, and this is your slow step. This is the price you have to pay, and reason why is you're breaking aromaticity. Getting this electrophile to add is the hard step. Once you've done this, once you've done anything to make this carbocation, loss of your H plus here, gives me back that double bond. In the next step, all I have to do is have some base. If that base can pluck off this proton, we give back that double bond, we regenerate our aromaticity. That's going to be our step down. So anything that helps us to stabilize these positive charges will make this more effective, or anything that makes the electrophile even more powerful will make this reaction possible. Those are your pieces that you're looking for this overall step. So step 2, picking off that proton, regenerating our arene, restoring my aromaticity is how we come out this other side. So it's a swap. You're taking E plus, whatever your electrophile is, and swapping it for H plus, your hydrogen, right? So it's in between those pieces. So that's the core mechanism. No matter what type of electrophile we apply, this is what's going on under the hood. So the thing you have to see as we go through these different ones, nitration, halogenation, alkylation, everything else, the only thing that's different is how you generate the electrophile or what the electrophile is. The core mechanism of how the electrophile adds follows what I just showed you there. That's going to be repeated for each one. The key thing you have to focus on is how do I take the bits that I put in, the stuff above and below the arrow, generate the key electrophile in order for us to initiate the steps that we just did. So let's start with nitration. Nitration, the nitro group, is this, NO2. What's your favorite aromatic nitro molecule? Everybody should probably know this. Something, something, nitro, tri-nitro, toluene, dynamite. Nitration is one of these molecules or reactions. Why this is so important is it actually comes from not only pharmaceutical, like we use this as a way of putting nitrogen into rings, but it's actually mainly driven by things from the explosive industry. That's how we know how these things work. So fun fact, if you're ever working in a lab with nitric acid and you just pour it down the drain along with organic material, you are making explosives in your drain. That's why you have to be very careful, especially with nitric acid, is it's not just a strong acid, it is an electrophile under the right conditions, and you have to handle it accordingly. So the conditions are HNO2 and sulfuric acid. So seriously, HNO3, nitric acid plus our very strong acid. What we're doing here is we're taking very, very, very powerful, very acidic conditions, and then this as our precursor. What's happening, though, is this HNO3, its job is to make that, our NO2+. That's the active electrophile in the system. Now look at the formula. HNO3, NO2+. What atoms are you missing? Oxygen and H. And what you'll notice is a lot of the times this is a common feature. I come in with a precursor, which is neutral, HNO3. I have to lose something like HO or hydroxide. That's not a good leaving group. So I'm going to run it with strong acid, which really what you're doing is H plus and OH minus. The combination of those two is they are related by the loss of water. Most of the time with these reactions, you're taking what your precursor material is, you're treating it with a strong acid, you're eliminating water to generate your powerful electrophile. You'll see a lot of the times we're following a similar procedure like this where some precursor is made more electrophilic in the course of the reaction by something like a strong acid addition, either Bronsted or Lewis acid. So how this nitro addition looks is like this. If I took HNO3, this is the Lewis dot structure of HNO3, right? It's got that formal negative positive, it's neutral overall. All I have to do is protonate this with my strong acid. That will make my ON double bond OH H plus, negative charge, positive charge. That closes, this comes out, and we generate with our N, double bond O, positive, and water. This is what we call fuming nitric acid. If you take nitric acid and sulfuric acid and you mix them together, again, this is one of those cases where whoever decided to do this was having a really bad day in the lab and was like, I'm going to take the two worst things I've ever had and I'm going to mix them together. But it protonates the nitric acid, you lose water from it, and you make this NO2 plus species. And it's balanced against by charge, right? You've got this sulfate minus. But that's the kind of the witch's brew that you're going to need to kick off this system, right? You've got this very powerful NO2 positive species. It's generated in low concentrations, and that, as long as the benzene is floating around in this will be our point. And that's why this is also possible. Molecules, most molecules, would be protonated under these conditions. If you have ketones, if you have aldehydes, if you have nitrogens, that's where the protons are going to be focused on. If you have just benzene, simple aromatics, they can withstand the super powerful conditions, the very acidic conditions we have for this. There's basically no choice left, but the proton is looking around for somewhere to go, and its choice is nitric acid, right? Of all the possible places to act as a base, nitric acid won. So this is where, again, relative pKa's that you're setting in here is very unique. So once you've generated this, the mechanism follows the general electrophilic aromatic substitution pathway we've seen from before. You start from here, you've used that dehydration to make your NO2+. We're going to use our double bond to attack this. Because it's so electrophilic, it's now a possibility. Remember, there's no proton that's going to protonate your benzene ring. That's not going to act as a positive point. But once we do this, we're going to make our resonance stabilized intermediate. Well, that's probably not better to draw it there. I'll put the positive over there. So we kicked off the electrons to make this, maybe a zwitterionic type compound. If this is in the presence of acid, you may even protonate that center temporarily. Oops, sorry. And then all we have to do is deprotonate this. Now, we need a base. Typically, we can write this as a base, any base that's possible in the system. This is kind of like SN1 reactions where the basic species could be your solvent. It could be whatever is actually still present in the system that's actually going to still carry out this overall transformation. Once we've added this, the base here from our previous step is probably the sulfate. So we're regenerating our acid catalyst to generate our nitroaromatic species. This is still going to be positively charged. Sorry. So this gives us a simple nitration. We're adding our electrophilic NO2 species into this. You can think of it almost like an addition to a carbonyl, and then we end up with our charged intermediate, loss of that proton. And again, it's acidic enough that even something like the sulfate anion is basic enough to pick off that proton, but think of it again kind of like our SN1 mechanisms. The proton is going to be transferred to anything else with enough electrons to allow this reaction to proceed. It'll be something with an oxygen or a nitrogen present in the system, and typically we would complete it with the anion that was available for generating the acid from the nitro step in the first place. So we need to do this only when we've got a very, very strong nucleophile. What you'll see, and we're going to talk about this later on, the consequence of adding a nitro to this ring here is very, very important. What do you think happens to this ring in terms of the electron density here compared to where we started out? Do I have less electron density now at the end of this reaction or more? Because the nitro group is a very powerful electron withdrawing group. Remember, if you draw this out, the formal charge on that nitrogen is actually positively charged. It's like you've got a positive or a permanent cation attached to the ring. That is a very powerful electron withdrawing characteristic to it. So one of the things that actually helps us in terms of control here, we start off with benzene. It's barely a nucleophile unless you've got something as powerful as like NO2 as your electrophile. When the reaction runs, you're going to produce a product which is now lower in electron density than we started out. That just means it's not going to go again. We add one nitro, and it's easier to stop at that point. Not saying you can't do polynitrations. It's just this is something where you're climbing a hill. Every nitro group or every electron withdrawing group you add is going to make the next addition even harder. So it's advantageous if you're trying to put only one nitro group in place, because the first one's easy, next one gets harder, third one gets almost impossible. But if you're trying to do this from a strategic point of view, one only, then you have a shot here. This is not like the case of reductions of your esters. Remember, reducing an ester produces a ketone, which is actually more reductive or more reactive to your reaction conditions. This is a case where you can hit it once and it will stop. Now, why the nitro is used, in addition to the whole explosive thing we talk about, it's one of your best ways of installing a nitrogen onto an aromatic ring. It's kind of like back to what we talked about with like a Gabriel synthesis. Even though I might want to put ammonia and react it together, ammonia is not the easiest thing to work with. Nitrogen, NH3, is not electrophilic, right? But if I take ammonia, I oxidize it, so I've got these two oxygens onto that group. It's carbon plus, or like nitrogen plus in the middle. I've changed its characteristic to make it electrophilic enough that I can do this reaction. I've set myself up so that this is now possible. So nitration is actually doable, but if we really want, in the end, your final product was to actually make the amine or the aniline compound, you have to do this one extra step of hydrogenation. So usually how we use nitration, we use the relatively easy generation of our NO2, relatively, right? It's fumic nitric acid. We add our nitro group to my arene ring, and then I will reduce those remaining oxygen bonds back to my hydrogens. And I have two general ways of doing it. We use nickel and hydrogen, what we call rainy nickel, but just hydrogen over these metal catalysts is what we typically can do for that first reduction. The other is what we call a dissolving metal reduction. So this is where we take strong acid, zinc, iron, something like a metal zero species that's doing a single atom radical reaction. Again, not something we're going to cover in terms of mechanism, but these are formulas that you guys should have available. The overall strategy in both cases is take a nitro group and turn it back into amine, so now I can do other chemistry. So this is a way kind of like our Gabriel synthesis where we're using a temporary form in order to carry out a reaction. Next one is sulfonation. So this is our sulfur equivalent of it. Like before, we put two species together, and again, you'll notice that the reaction conditions in this case, sulfuric acid, is all we really need for this reaction to happen. I can take sulfuric acid, what we call fuming sulfuric acid, where if it's acidic enough, we've pumped in other electrons, or we've got it concentrated enough, it'll actually have a gas kind of bubbling off it. And this is usually SO3. So SO3 is a gas that can be produced, but once again, look at your formula. H2SO4 relating to SO3, the only difference between the two is loss of water. So if you take H2SO4, sulfuric acid, and it's so concentrated, so acidic, that you actually lose or dehydrate it, lose water, the other part of the product here would be SO3. Once we've got our SO3 and we protonate that SO3, that gives us our electrophilic species, this HSO3+, that is our active electrophile in this system. So super concentrated H2SO4 gives us access to this molecule, which gives us the sulfonation. In the end, it's very similar to our nitration. So imagine here, first thing I'm going to do is take sulfuric acid plus a proton, and I can generate SO3. That's where you draw it as a Lewis-Strauss structure like this. To activate it, all I'm doing is protonation of that to give me my OH plus and sulfate. The other resonance isomer, you could draw this one, looks like OH, where I'm just putting the charge directly on the sulfur center. We're just trying to emphasize this is an electrophilic sulfur species. The same way the other one was nitric acid losing water gives me an electrophilic nitro species. Similar in concept, right? Heteroatom in the middle is positively charged. You've got oxygens around it that's drawing off that charge and stabilizing it. Makes the center here super, super, super electropositive. And again, how we get it is just two molecules of H2SO4. One of them, once you lose water, is just condensing down, gives you the structure you're seeing here. Same mechanism. Protonate one of the OHs, loss of that OH by condensation. So this gives us our electrophilic species. This is the sulfur center that we're going to do for our actual electrophilic addition. And it follows the same logic we did at the very beginning. Double bond in our benzene is our parent nucleophile. That's going to attack this center, and we're going to move the charge density out to the outside. Well, I'm going to draw it as the delocalized one again. Positively charged, H, S, double bond, OH. And remember, to form this species, the ion we're balancing it by, once again, is our sulfate ion. So if that's our base, we regenerate our sulfate. So these benzene sulfonate compounds, again, formed in a similar way as what we've done for our nitration. Only difference is starting from only sulfuric acid, just if that's the only species there, it would form our SO3 type reagent. That SO3 reagent under the strongly acidic environment is activated, nucleophilically attacked by our benzene, and then coupling into here. Now this does give us a level of control. If I only have sulfuric acid, I will sulfate something. If I have a mixture of nitrate and sulfate, I will nitrate things primarily. So this is something where the addition or subtraction of those two species, in general, the nitro compound is a more electrophilic species. That will be my preferential system that I'm going to be forming as an electrophile. In the absence of that nitric acid, sulfuric acid only, then I'm doing a sulfate chemistry. But it's really the addition or subtraction of those two species that allows me to dictate the chemistries that I'm happening. So that's how we add these strongly points. And again, sorry, just as a statement again, remember we talked about before, if this was a nitro compound, this is a strong electron withdrawing group. Benzene is a more nucleophilic species. We're making a deactivated or a now electron poor arene. What about sulfate? Are you making something that's more electron rich or less electron rich? What do you think? Less? Any more? Why less?
Because it's also got the heteroatom with the double bonded to the two oxygens and hydroxyl.
Yep. Sulfur on its own is already electronegative, right? So polarization is already towards sulfur. Plus you've got three other, well, if you count them, right, that's 1, 2, 3, 4, 5 oxygen bonds effectively. All that is hauling electron density as well. Very much the same idea, right? This is a strong electron withdrawing group, so you're making a relatively stabilized or unreactive system. So single sulfation is possible. Single nitration is possible under these conditions. Yep, same idea as nitration. The other really, really important one, and why this matters, if anybody's heard of things like Suzuki reactions, cross-coupling, a little bit, this is one of the most, seriously, it was only the last 15 years. And actually 3 years ago, I think the Nobel Prize was given for the discovery of things like the Heck reaction, Suzuki reaction, cross-coupling. We use this reaction religiously now. And the Suzuki reaction as a starting material requires aryl halides. So aryl halides are so important. Taking a benzene and reformatting it into an electrophilic material is really, really what we need to be able to do. So these kinds of reactions are actually foundation where we can take simple arenes and reformat them by addition. So, how these reactions work is we're going to be adding our halogen component. Typically, how we're doing this is we got to go back to our primary base halogens, chlorine, bromine, or iodine, are what we're going into. Now, unfortunately, just as this goes back to what you've seen for double bonds, I can take a double bond with bromine, and that should add Br across the double bond. One is bromine plus and one is bromine minus, right? That's your typical one that you've seen for those components. If I do this addition, and if I add bromine to my benzene, nothing's going to happen. On its own, the arenes are resistant to bromine as it is. But we have to add another catalyst to it. In this case, what we're going to be doing is adding an iron species to it. Iron's not added across this, but it's the addition of these components on its own. And the mixture that we generate is what actually allows this whole process to happen. So this is a case where we're creating a large witch's brew where all the species have to be put together to generate the overall, active components of the system. Iron on its own is actually going to take the first move and react to make iron tribromide, or in the case of chlorine, iron trichloride. These become what we're strong, super, super, super reactive Lewis acids. So this is where we're crossing over. Remember, Bronsted acids are proton donors or electron acceptors. The Lewis acidity is what we're really tracking here, and we're focusing on the activation of the arene or activation in the case of the halogens as well. So we have to make these, and that's why it's this mix of the halogen plus iron. These are just two easy precursors. The reason why is, again, iron trichloride, iron tribromide, they're ridiculously reactive compounds, hard to hold in a vial, much easier to take the two components, form it when you need it, and then do the reaction. So what you'll see as a condition is your parent arene, bromine, iron, and then you're doing your generation. Final product here is still this overall functionalization plus your iron tribromide species, which gets worked up, usually becomes iron hydroxide at the end of the reaction. This is our catalyst species that just does for mass balance. So there's two parts that we have to do here. Iron and bromine on it together. If we do this out, this is an oxidation reduction chemistry, where the point you just have to focus on, it's a simple balanced chemical equation is 2 irons and 3 Br2s eventually give us 2 molecules of iron tribromide. This is a disproportionation and redox chemistry to give you basically iron 3 in the middle, and then the Br, which goes from neutral Br2 into Br minus. And that gives you this iron tribromide complex. And again, if you're going to draw it out, we got it down here. You think of this as at the center, this is an iron 3 complex or iron 3 plus, where each of these is equivalent to a Br minus. So the overall complex is neutral because what we've done is take this iron in the middle, we make it a 3 plus system, and we have Br around its periphery. What that does, iron in the middle is ridiculously electrophilic on its own. what we having this 3+ in the center here, it is a strong Lewis acid. Remember, Lewis acids are electron acceptors, and it's the combination where these high valent metals are actually, we're still at the intermediate. Iron tribromide on its own can't still play with directly with the arene. It's not that electrophilic, but it's definitely electrophilic enough to take your Br2 and supercharge it. So Br2, remember, we can think of this as either, and when we do our normal additions, we would think of the bromine as one end of it being sort of a Br minus, and the other end being our Br plus, right? How we've done our additions with bromine to things like double bonds is we would usually attack bromine, adding one of the centers to give you a Br plus kind of character, ejecting the Br minus. And that's if we were to think of this in terms of a heterolytic bond type cleavage. So all we're doing here is taking our normal iron tribromine complex. Remember, this is neutral. It is initially super electrophilic in the middle, and that's the consequence of this 3+ kind of character. I take bromine, which has all these electron densities, and I can polarize it by effectively adding to the center here to make what we call a dative or coordinative complex. I took Br2 and I cap bromine on the end of it, and what it's doing is basically like, look, we're not doing anything yet, but we are conspiring. What we're doing is the bromine here is now bound in this place. We get this sort of polarization, and what that happens is this end here is now super electropositive. You've basically supercharged it where you're already ready to pick off that bromine, and you've left the other one as your exposed electrophilic center. So it's this overall cascade complex that makes your electrophilic center for your halogenation. We need to do these two steps. And this is where, again, reactions, you can do this part before. If I take benzene and bromine, they look at you, nothing happens. Benzene and iron, nothing happens. Benzene and Fe, Br3, nothing happens. But this combination of all the species lines things up to make the intermediates, an intermediate like this in particular, that is your supercharged electrophile for the reaction to occur. So now that we've got this coordinate complex where iron tribromide's job is to grab the reactive but still innocuous Br2, it's going to supercharge it. So now we have enough energy built into the system to allow nucleophilic attack on our bromine and then displacement of that bond. The purpose of this is to basically make effectively Br plus completely without anything else to support it. It's a very electrophilic form of Br plus effectively. So the intermediate we can generate from here. Same smiley alien, Br, and you can think of this as Fe Br4 minus. It's an iron minus type complex because what we've done is we've pulled those electron densities over to that system. So once we've got that, you can think of this, either the bromide or this complex itself is our base to regenerate our complex, regenerate our aromaticity. So we get HBr, Fe Br3, where again, Fe Br3 is so electrophilic. Once you treat it with water, water will break this complex up to its ionic components, iron 3 and hydroxide. So it's usually iron hydroxide or a bromide component once you actually work it up. This is the piece here we have to sort of deal with on workup. H2O gives us FeOH3 Br minus and H plus. So that's the ChemDraw component. So the sequence that you're seeing here should start to become familiar. Every one of these reactions starts off with saying, I need to make special conditions a very electrophilic species. In nitration, I'm using acid to lose water. In sulfonation, acid to lose water. When you go now to bromination or chlorination, I'm going to form my Lewis acid, which is then going to allow this polarization. Once you've got your very electrophilic species, nucleophilic addition gives you this delocalized carbocation, which then H proton loss gives you back your arene. So the pattern that we're working through here is going to be the same. So this general mechanism works for adding bromine to our arene. If we were going to be adding chlorine, we would just use Cl2 plus usually Fe Cl3. So that would end up being our mixture, and the exact same mechanism you see above here to give us our aromatic chlorine. So one thing I wanted to clear up about the last slide we discussed, which was the iodination of benzene. So while we can use that sort of neutral halogen plus the, let's say, the halogen equivalent is the iodine, the strong Lewis acid component. When we try to do this for iodine, this does not really work. This reagent is very, very reactive and typically does other chemistry. In addition, iodine has a different redox potential, so there's more complex reactions it can do. So we don't usually have the exact same analogous reactions we had for chlorine and bromine using sort of that iron catalyst. Instead, if we're trying to insert iodine in there, we can use a different mechanism where we oxidize the iodine with some species like nitric acid in order to give us our I+ reagent. So you can think of this where, for example, what you have is I+ and then some very stabilized anion that is acting as a counterpoint. You would typically form this. Another good example would be something like ICl, where you can think of that as I+, Cl-. So these reagents, really what you're doing is converting the normally anionic halogen into its more oxidized form as this cationic electrophile. Another reagent that we typically use is this acetyl hypoiodate with the formula you see here. So what this looks like is if I have benzene and I'm aiming to make the iodinated benzene, you would typically use a reagent like, for example, ICl or CH3, CHOOI, where both of these are, think of them as sources of iodine plus that we would use to carry out the iodine electrophilic insertion to benzene. Same mechanism we've seen before, though. Now for the try it later, we're asking you to sketch a generic reaction coordinate diagram for the electrophilic aromatic substitution, labeling the sigma complex that we form. Hey, what's up, guys? So I'm going to go through some of the after lecture notes. I want to clear up one point that people mentioned, which really it's in context of where this electrophile comes from when dealing with the sulfonation mechanism. So we mentioned that it's a dehydration product of sulfuric acid. So all you really have to do to make it is have very concentrated sulfuric acid, and it's one with another. So imagine one of these molecules or two molecules of H2SO4 could be used where one is acting as the acid donor and one is the product. So all you're doing here is imagine one of these picks off a proton from its partner. That's going to get you your sulfate, like that. And you've got your protonated sulfuric acid, H2 plus OH. And then that can now eliminate water to create SO, O, and then H plus, and then after loss of a proton, so if we were to borrow that proton back, that's going to generate our SO3 gas. So this is a consequence of very, very concentrated sulfuric acid. If you just have this with very little water around, this kind of self-ionization pathway starts to kick in. It starts to actually gas or generate SO3 spontaneously. That's where we get this name, fuming sulfuric acid. So if it's concentrated enough, what you're just observing is that this SO3 gas is just spontaneously being generated and kind of boiling out of it. Once you have it, once it's generated, it can be further activated to make this electrophilic form. That's our proton transfer to give us our SO3 plus species, where remember we said by resonance that can sort of be thought of as an analog to our nitration, right? So this is our electrophilic core, which back to
the analogy we showed you before, the nitration or the nitro electrophile looks like this. So it's very strongly electrophilic at the center heteroatom here. Okay, for the try it later, what we're asking you to do is sketch a generic reaction coordinate diagram for electrophilic aromatic substitution, labeling where that sigma complex is going to sit. That's the cationic intermediate that we generate on the path for the aromatic substitution reaction. Now, we want you to kind of go through for each of the ones we've shown, nitration, sulfonation, halogenation, sketching this reaction coordinate diagram, drawing the structures that you might see, and trying to be as explicit as this to really kind of ground all the different things that might be happening. So in general, right, the overall generic mechanism, right, is our aromatic compound, some very powerful electrophile forms our sigma complex. This is where we've temporarily broken aromaticity, so you can show it as a delocalized complex. I'm going to show it as explicit, where we have our cationic center, hydrogen, and your electrophile. So cationic center adjacent to where the electrophile has been added. And then we lose our proton to give us our electrophile and the proton, regenerating this. So if we were to sketch this out, you could imagine that my energy is going to be on this axis, and then the reaction progression is along our x-axis. We're starting at some benzene on its own, and we're going to mix in some type of electrophile. So you can imagine this species here might sit at some elevated level, where it's the complex where we have both the benzene and our electrophile. We're going to go to some very high energy intermediate, where that barrier is our rate determining step. It's kind of like an SN1 reaction, where up here is our sigma complex. Sigma complex is sitting at this elevated point because we're at a very high energy state and we've broken aromaticity. There's a relatively narrow barrier down to our products over here. And there's a couple reasons that we're putting the products, sorry, let me just, look at that. Putting the products down here overall as a delta G naught downhill, that's reflecting that we're starting with a very high energy electrophile and we're generating a proton. So the energetic thermodynamics of the system is still driving towards a more stable state where we are consuming the electrophile. The sigma complex sits right there, is a high energy intermediate, much like the carbocations we've seen before. And the part we're trying to emphasize is that right there, this delta G double dagger is a rate determining step. That's our transition state that we have to get to that controls how fast the overall process is going to move. So next, if we wanted to look at each species, let's say the nitration, sulfonation, halogenation, we could potentially make this a little bit more detailed. If we started off with, let's say, benzene on its own plus nitric acid, HNO3, plus sulfuric acid, let's say, H2SO4. So this is the mixture of material that we would go into this system right here. These are each relatively stable materials. So we're going to start as a baseline where all components that we're going in for our nitration, let me just redraw that a little bit less. I'm going to stack them up, but energy levels right here, and that's this HNO3 and our H2SO4, and that's at this level right here. Now we're going to do a dehydration. I'm going to put that dehydration slightly uphill, and all we did here is we still at this first preliminary intermediate, benzene is still benzene, we haven't touched it yet. We have, let's say, protonated the sulfuric acid, or excuse me, protonated the nitric acid and eliminated it. We've made our NO2 cation with our corresponding HSO4 minus anion. So now we've generated our electrophile. We're at some elevated temporarily state that is now primed for our next step. So that now goes to our sigma complex. This would have a structure for nitration where we have our cation NO2 and H. And then we have our return. And then all of the components for mass balance are also in this complex. So we still have our water and we still have our sulfate at that point too, just for clarity in terms of writing it out. I'm omitting it here just for space, but everything, the way that you sort of draw this out is all atoms that you start with are being carried forward at each one of these steps. So up here, we still have our water, we have our sulfate as our balancing anion, and then after the reaction is complete, we want to draw this where we're at some lower level, so we're much downhill. At least the overall delta G here, definitely the delta G from that elevated step, delta G naught from this step down to our product is part of our driving force overall here. So we're going to have our our aromatic nitro, NO2, and H2SO4 and water as our overall components that we've kind of built out. So this is trying to reflect that rate limiting step is this one right here. This is our delta G double dagger up to our transition state, our sigma complex. And the overall driving force after forming this one is still in favor of getting over to our product and regenerating aromaticity. If we want to try the same thing with sulfation, you'll see very much the same type of steps as we did with previous. So once again, let's put a level down here. This is our benzene. And we've got 2 molecules of H2SO4. And we're going to have some slight elevation up to here where we're generating benzene, H2O, SO3, and we still have, let's say, 1 H2SO4 left over. So now we've got this intermediate. Once again, we go up to our sigma complex. This would have the structure of, cation H SO3 H, right? We're going to protonate. Actually, why don't we draw that explicitly? So after we've generated the SO3, we're going to make one more elevated intermediate up here, where we're going to do a proton transfer onto the SO3 first. So here, we've got benzene, HSO3 plus, that's our electrophile, HSO4 minus, the counter ion, and water still in the mix. So this is now walking up the energetics so that we have our electrophile species. So what we've done is an elimination of water followed by the protonation to get our pre-electrophile. Now the big jump here, this is still our delta G double dagger associated with getting up to up here is our sigma complex. HSO3H up here. And then we're going to go, so just for, we have one more transition state, and down to our product where we have our sulfated benzene, SO3H, and again regenerated H2SO4 and water overall. So once again, we're trying to show that the delta G from some elevated state here is still going to be driving forward. Whether or not the overall delta G from where we started out here, I'm not trying to emphasize that. I think that's debatable depending on which group you actually have. But the definite one here, as we move through the electrophilic substitution from whatever elevated electrophile, there's definitely thermodynamic driving force to go from these more unstable electrophiles to the final reformed state and it ejecting things like water to make stabilized species. Okay, so for this last one, halogenation, a couple more or just a little bit different combination of steps. Let's say we start off with, once again, benzene. We're going to start with 1 molecule of iron, and we need Br2. So all these components are in here at this energy level. Now for the stoichiometry, overall we have to make 1 molecule of Br3, and then we're going to add a Br2 to it as well. So we're actually using 5 atoms of bromine. So coming from Br2, that's equivalent of 2.5 bromines, Br2s I mean. So by putting that together, the very first thing that's going to happen is the generation of our Lewis acid. So at this elevated step, we haven't done the addition yet to our bromine. We've still, or to our aromatic, we've got our benzene. We've made, at this point, FeBr3, and we still have 1 molecule of Br2 left over. So we're at a higher energy state, but we're not quite ready to go just yet. That's where these guys can coordinate together. And we're going to get an elevated step up here. Still, benzene hasn't joined the party yet. We've got now our complex, which we would draw as Br bound to FeBr3, right? That's the one we drew out. Think of this as really, really electrophilic over here. This is kind of a composite anion, which makes this Br+. So again, bonding, we've got 1 Br bound to Br. We've got a coordinate bond here to our Lewis acid, which is our FeBr3, like that. So that's the bonding components of it all. But energetically, this bond here polarizes, this bond right here polarizes our bromine component. So you can kind of put a box around this, assume this is going to become a anion, which makes this our Br plus effectively. But this overall coordinate complex, neutral overall, is our now elevated or activated electrophile for the system. Once we've got that, that's where we can engage to make our sigma complex. This is where we've got our aromatic ring, H bromine cation, which is balanced against FeBr4 minus. And then that's going to go downhill to our brominated aromatic, our HBr, and FeBr3. Once again, you're going to look at this as our delta G double dagger for the rate limit determining step. Again, we're downhill in energy from whatever this energetic one is. This is our delta G naught for the system. And it's this driving force here that gives us our thermodynamic bias as well.